verifier. So
is this a consequence of the verifier or the problem? I mean, this looks like constant propagation to me.
It's a consequence of the problem, but the problem is that the verifier itself requires that you be able to process this kind of stuff.
But you could do a different algorithm, which would be quadratic.
You could do a different algorithm.
Yes.
And actually, we just submitted a different algorithm to Popple that was based on SSA generation first, but it was rejected. And people, and in general, people have been saying this is not a problem, so it's not relevant enough. Okay, so I'm just going to quickly go. And so, as I said, we have a little tool that generates difficult to verify bytecode files, and when you use it, you can see, oh, you have this wonderful quadratic curve. In their ultimate wisdom, some people actually limited the size of a single method in Java to 64K. Right? So because if it was longer, you could get this much nicer quadratic effect. But then there's also this very nice thing that's called a jar file. And with a jar file, I can get like a 3.5 kilobyte jar file that takes 15 minutes to verify. And our little tool actually tells you just tell it how long do you want your verification to last. And it generates you a little bytecode file that takes that long to verify on a 3 gigahertz Pentium. And then you see, with a jar file, this curve is much steeper. Now, if you want to see it, this is actually a little website. So what's there is an applet that will eventually verify as being correct, but it will take 15 minutes on a 3 gigahertz Pentium 4 until you get back, the thing that says it's correct. And of course, you can't. The only way you can stop this is kill your browser, because there's currently no way to actually even stop verification in the Java in any Java browser known to me. Okay. Now. The CLR is better, actually, because the CLR has an empty.
Can you roll back the slides so you can copy them?
Oh, I'll give it to you later. There may be other ones. So the interesting thing is, why stop at the verifier? Because in fact, there's lots of nice problems in compilation that we know are NP complete. So I could actually, if I know what the implementation of your compiler is, I might be able to feed you a puzzle that just exhibits, the worst kind of complexity or something.
So, Michael, I mean, many dynamic compilers just have a timeout.
Yeah.
So they just bail out if it's takes, especially dynamic compilers.
Yeah, sure.
They have a cost. So
but the problem is you can't bail out of verification.
No, yeah, I know, but I'm talking about register allocation, instruction scheduling.
Okay.
No, the comment was for register allocation and instruction scheduling.
Well, so right now I'm just trying to talk about the robustness of the whole scheme. So, the new thing is that what we should really be doing when we want to harden this stuff is we should actually optimize for the worst case performance, and nobody is doing that. Everyone is sort of trying to optimize for average performance. And that might all be very well if you're doing this for a machine that's sitting on your desktop, but it may not be good if you actually put the verifier underneath, or if you have a unattended server virtual machine. Yes?
Speaking as someone who has worked on compilers that made it into production, we do worry about the worst case.
Okay.
And we do. There are safety valves and time limits and all sorts of things. Because it's really embarrassing when it runs for 3 days. And you hear about it.
Okay. So I'm glad to hear that.
It's not intentional.
You have another guess?
I'm not quite sure I understand how you're phrasing the problem here, because you don't have any control over the actual runtime of the resulting code anyway. So I mean, in some sense, in most Java applications, it's easy to launch a denial of service attack because you just write an infinite loop, right? But so in what way is this different?
So the problem is that you're really doing this at a stage where before your real resource management fully kicks in, right? So, and right now people who are building compilers don't seem to be worrying that much. But I'm glad, my vision is just trying to verify everything, and I'm just trying to say, show some cases where you actually need to worry about something else. And of course, then the other problem is when you're doing this open source, you're actually telling people exactly how your algorithm works, which makes it much easier for people to actually come up with an exploit. Because, and the problem is fixing, so these are not programming bugs, right? These are actually fundamental characteristics of what's going on in your compiler, and hence, changing it if you have an exploit is much more difficult, because you actually have to change the algorithm, and you're doing this under the scrutiny of your attacker.
But you're paranoid too.
Of course.
And so an obvious thing to do is to have, for instance, there's some good analyses that are statistical if you feel lucky. The paper from Berkeley, the probabilistic data flow.
The probabilistic equivalence finding stuff.
And so what you want to do there is you would actually start your compiler with a random seed, and part of its output in the object file would be, by the way, here's the seed I started with, just in case you need to reproduce this for debugging. But obviously, we should be doing more of this and always making random decisions.
I'm just trying to be controversial here, so.
Okay, but we.
Yes.
You're focusing a lot on some of the basic safety properties that you get from type safety and the kinds of, and these are the properties that the verifier verifies. But it seems to me that the difficult problems are not these. The difficult problems are, or rather, the difficult problems that matter in practice are not these. Because what is the point of trying to enforce safety on an operating system? You cannot protect the operating system from doing anything it wants with its own resources. Right? So the only thing you can, because there are way too many interfaces and internal details that cannot be controlled.
That is true, but the thing is, I'm trying to also try to get around these intentional backdoors.
Yes,
So, yeah.
That's the thing I don't understand. I'm an OS, I have perfect rights to reformat the disk. That's not a verification error to send that. My exploit is to add a line when it receives a packet to reformat the disk. It's all verifies fine, but it destroys the system.
Right. And there are lots more of those in Java applications that people, my example of showing threads. Showing threads is a terrible thing. It ought not pass a verifier, but it does.
Okay, so you would have to solve those by having some higher level type systems that have more descriptive, yeah. Okay.
One use of this is to isolate multiple OSs. I don't know how VMN do it, but one use of what you're talking about is to isolate multiple running versions of multiple operating systems running on the same kind of monitor. And I don't know how the virtual machine monitors do it. They must have presumably you have a solution, but I don't know what
Yeah,
kind
you
of solution
use the hardware protection mechanisms to isolate.
Regardless, this isn't necessarily a solution for all the problems.
Right.
It's
So
a solution for a class of problems.
So let me go on a little bit. So we had this, and now I'm trying to talk. How do you actually build such a thing? And I probably won't get through it. So we need a small, inefficient, safe code foundation that is actually small enough to be verified manually. And then efficient enough to support an OS running on top. And what I'm claiming is that the current options don't fall short. So virtual machines with interpreters are obviously too slow. Virtual machines with just-in-time compilers, the compiler gets too big if you want to do a great job. And proof-carrying code has the problem that the code proofs are huge and not portable. So what we've been working on is we've been working on virtual machines that are targeted at minimizing the size of a proof that covers the rest of the semantic distance. So this is trying to raise the abstractions. So I'm actually going to show you a picture. So if you look at a JVM, the blue line is where the stuff becomes concrete. So in JVM, you compile to something quite high level, and then you cover the semantic distance with dynamic compilation at runtime. In proof-carrying code, you actually cover the semantic distance with static compilation, and you do proofs to cover that and ship the proof. And that proof is very large and very complex. I mean, if you look at Nicholas' thesis, it takes him several pages to prove that an integer is an integer and a Boolean is a Boolean. And now the question is, can you come up with a virtual machine in which the virtual machine creates higher level abstractions that make the proofs very easy, and yet while having the facility to have very efficient compilation to binary code. And that's what we've been trying to work on. So a hybrid system where you actually use a combination of things. The interesting thing is that Andy is no longer here. Andrew Appel has been going exactly the other way. He's been trying to lower the semantic level of the thing that the